Well, hello there. Time to do some Chapter 15, Dynamics. And in this chapter, we are dealing with general plane motion. And we had a video earlier in this section that talked about general plane motion and how we use the equation for relative velocity with the equation for velocity for something traveling around a point. So velocity is r omega. All right. In this problem, at this point in time, this device is rotating with bar AB having an angular velocity of 4 radians per second. 4 radians per second, clockwise. And the question is, at this instant, what is the angular velocity of omega BD and omega DE? And we will go through and solve that problem. We start with some given information. In the picture, the length of bar AB is 7 inches. The length of bar BD is 8 inches. The length of bar DE, we need to use a little Pythagorean theorem, 11 squared plus 3 squared, square root, to get 11.4 inches. And while many of the parts in this linkage are both rotating and translating, point A on bar AB and point E on bar DE are not translating. Those are fixed points. So they have VA and VE of 0, but there is rotation. So again, find omega BD and omega DE. I'm going to zoom in a little bit to give me some place to write. And what we start with is that the velocity at point B is equal to the velocity at point A plus the velocity at B with respect to A, which will be nothing more than the radius of AB, the length of AB, and omega AB. And those are both given. The length was 7, the omega is 4. So at this point in time, VB has a perfectly vertical velocity of 28 inches per second. Now, point B is that special point in common between linkage AB and linkage BD. So we can actually now use the general plane motion equation to say that the velocity at D, right here, for linkage BD is the velocity at B given plus the length of B times omega BD. Same equation, same relative velocity equation. And in this, VB is 28 inches per second up. And I'm going to change colors so I can make a point here. V D with respect to B will be perpendicular to the RBD line. And perpendicular to that vertical line is horizontal. So the length is 8. The omega we don't know, but we do know that it will be horizontal. So we have, for VD, we have two things going on here. A 28 up and an 8 omega BD to the right. So what we did here is we found the velocity at D coming from point B. Well, D is also a special point in that it is the one point in common between BD and DE. So we can write the equation for VD coming down from point B, which we did, and now we can do it coming up from point E. So VD equals VE plus the length of that bar times its angular speed. Well, VE is a fixed point, so VE is 0. RDE is, I've got this written wrong, RDE is 11.4 omega DE. So we have to figure out for that VD how much of this VD is in the x direction. So I'm just going to draw this right here. This is, oops, that's a bad drawing. This is bar DE. And we know that the velocity will be perpendicular to the rotation. We need to find that angle so that we can find out how much of this VD is in the x direction and how much is in the y direction. So we're going to need that angle. Well, we can use some trigonometry. We were given enough information to know that this was 3 inches and this was 11 inches. Oops, no, this is 7 inches, sorry. No, it really is 11 inches. From E to D is 11 inches. So that is 11 inches. I need to do some erasing down there. Go away, go away. So I need to take my calculator out and say, well, what is the inverse tangent of 3 over 11? So coming over here, grabbing the calculator off the iPhone, flipping it sideways, 3 divided by 11 equals inverse tangent 15.3 degrees. And if that's 15.3 degrees, then this is 15.3 degrees. And if this is perpendicular, then the angle here is 90 minus 15.3, or 74.7. So 74.7 degrees is this 11.4 omega DE. That is at an angle of 74.7 from the horizontal. So if I want to know how much of that 11.4 omega DE is in the vertical direction, it's going to be 11.4 omega DE times the sine of 74.7. And if I want to know how much is horizontal, so the vertical component was the sine of 74.7 times 11.4 times omega. So 11.4 is the length. Omega is the angular speed. That gives us our velocity. And that times the sine of 74.7 is the vertical part. And that times the cosine of 74.7 is the horizontal part. So now we have found VD twice. Once coming from point B, once coming from point D. We have two unknowns here. We don't know omega BD, and we don't know omega dE. And our two equations are the vertical parts, the 28, and the 11.4 omega dE times the sine of 74.7. So the vertical part of the 28 equals the vertical part of 11.4 omega dE sine 74.7. So now I need to say omega dE is 28 divided by 11.4 divided by the sine of 74.7 equals 2.55 radians per second. Now my second equation, let me just grab this goofy color, is going to be that the horizontal part of the one equation equals the horizontal part of the other equation, or the 8 omega BD equals the 11.4 omega DE times the cosine of 74.7. And we take this 2.55 and substitute it in there. So I'm going to do the math now. 2.55 times 11.4 times the cosine of 74.7 divided by 8 equals 0.957 radians per second. So there are our answers. 2.55 radians per second for omega dE and 0.957 radians per second for omega BD. We need to look and see if what the directions are. We can see that omega dE right here has to be going clockwise, so omega dE is clockwise. And for that to happen, omega dE must be going counterclockwise, so counterclockwise. In summary, what do? We used the general plane motion equation once, twice, 3 times to identify our unknowns, which were omega BD and omega DE, and we used the fact that the vertical parts of 2 equations must equal one another, and the horizontal parts of 2 equations must equal one another. The end.